always work as you expect it to. And my first thought was, this must be a glitch in JavaScript. But upon further investigation, that could not have been further from the truth. So before we dive into how computers store numbers and why issues like this might arise, a quick reminder of the difference between decimal and binary and how arbitrary they are. So the reason that we're used to thinking of numbers in decimal form is simply because we have 10 fingers. And so for our ancestors, your fingers were your computers. And the reason that computers, on the other hand, store information in binary is because they use circuits as their base form of logic, which have two states, on or off. But you could store numbers in any number of base systems. For example, cultures that didn't wear shoes often had base 20 number systems for your hands and toes. So to represent 2016 in both base 10 and base 2, I've laid it out just to clarify. So each part of the digit string is simply the number there raised to the base, times the base raised to the power of the place of that number in the string. So these are both finite representations. 2016 is representable in base 10 and base 2 as a finite expansion. On the other hand, 1/10, while it's finitely represented as an expansion in base 10, cannot be finitely represented in binary. And this might seem strange, but we don't think of it as strange when numbers can't be represented finitely in base 10. So for example, 1/3 can't be represented as an expansion in base 10 system. So a floating point is a system of storing numbers, and it will look familiar if you've ever worked with scientific notation. It's very similar. So it consists of the significand times the base raised to the exponent. A few examples are listed there. The significand is also called the mantissa. It can be either positive or negative. It has a radix point, and its length determines how precision the number will be. How precise the number is stored. So if you have more digits, you can store a more precise representation of the number. The base is typically 2, 10, or 16. You may have seen hexadecimal when working with certain representations of colors for CSS. And this will determine which fractions have terminating expansions. The exponent can also be positive or negative, and this will determine how much the radix point has to shift so that it can be represented with the radix point after the first non-zero number. So this is nothing new, just a quick blast to the past. These lovely gentlemen were using a floating point in some of our earliest computers. So on the left is one of the first programmable calculators, and then on the right is one of the first computers which uses punch cards, and these both implement floating point. Today, however, the IEE has implemented a standard for floating point arithmetic, 754, and this is what virtually all machines currently use to store numbers. So there are several different precision levels that you can specify numbers to be stored at. There is single, which takes up 32 bits, in which the sign will take up 1 bit, positive or negative, the exponent will take up 8 bits, and then the fraction, which is the mantissa minus the radix point, will take up 23. So it's normalized before it's stored this way so that you can always assume where the radix point is, and then the exponent can be adjusted accordingly. The exponent's always stored as a positive number using a bias, similar to how in Kelvin temperatures you can have absolute zero. You never have to represent a number as negative, so it's adjusted that way. This might help explain some strange programming special things that might have arisen when you've tried to set not a number equal to not a number, or positive or negative 0. So these are stored specially in IE 754. And so there are actually multiple ways that you can store not a number. It can be either positive or negative, and it can actually carry a payload in the fraction, which will have information about what kind of invalid number has occurred. So naturally, when you're trying to store something that is potentially infinite in a finite amount of space, there will be rounding and some rounding issues. So there's a rule in IEE 754 that if you're rounding between two values that are equidistant, you actually round to the even digit. So this is somewhat arbitrary. And because you're rounding these numbers, when you perform more than one arithmetical operation on them, the errors can be cumulative. So the more operations you're chaining together, the more error-prone this type of math can be. So in order to deal with this, there are several strategies. So one can write algorithms that would save intermediate results at a higher precision than that which you want the result to be. So as I showed you a few slides ago, there's double precision as well as quadruple. So for example, if you knew you needed your answer to be of a double level of precision, you could store your intermediate numbers as quadruple to prevent the final answer from being too off base. There's an entire field called numerical analysis, which deals with numerically stable algorithms, which are algorithms specifically designed to decrease the rounding errors that can happen this way. Also, in other languages such as C# and Python, there's a special decimal data type that allows you to kind of overwrite the way numbers are stored, usually in JavaScript, and actually store them as a decimal, which is how financial software deals with storing information about money precisely. But the most common way to deal with this is to just use a library that allows for higher precision so that you can specify how precise you need your numbers to be stored. So in JavaScript, you don't have much say in how your numbers are stored. They are all floating point double precision, whereas other languages, if you've worked with floats or halves or doubles or longs, you can specify how much information you need to be stored about a given number. So there are a couple of libraries that let you deal with very large or very small numbers when precision is important to you, such as Sinful.js and Math.js. And I will quickly show you how to use Math.js. So I wrote out a little script, and because this can run in the browser as well as the server, we're just going to do some quick math. So 1/10 plus 2/10 using vanilla JavaScript, and then the same but using Math.js's big number type. And so rendered here, you can see that we have the error from the title slide, but using the big number data type, we get 0.3 as expected. Here's some further reading if you should have an interest in this, and thank you for your time.